Today we're going to look at sequences and series. We're going to define what we mean by a sequence and sequence notation. We're going to see how we can write down recursive and explicit formulas for sequences, graph sequences, do some pattern recognition. We're going to define summation and product notation and use that to help us define a series. So a finite sequence of length n is a function whose domain is the first n natural numbers, or sometimes we'll start with 0, so it'll be the whole numbers. The range can be anything. Sometimes they're also natural numbers, but they could be real numbers, complex numbers, or they could be some kind of something else completely, like shapes or something. An infinite sequence is a function whose domain is a set of natural numbers, the entire set of natural numbers, or sometimes we'll set it up as the set of whole numbers instead. So notice that we've got all relations. Functions are a special kind of relation, and a sequence is a special kind of function, sort of a different way to go than the one-to-one functions that we looked at earlier. So the sequences basically, we have the inputs are 1, 2, 3, 4, 5, and they go up to a certain number and stop, or they go on forever, but you can basically count off the points, 1, 2, 3, 4, and so forth. So basically we have a function, for example, that maps the natural numbers into the natural numbers by the rule f of x equals 2x. This would be how we might write it for a general function. But in sequences we often make some changes in the notation. So typically when we have functions and relations in general, we have a tendency to use letters like x and y. And for the names of functions, we have a tendency to use letters sort of like F, G, and H in that part of the alphabet. When we have sequences, we usually use letters like I, J, K, L, M, N from that part of the alphabet for the input instead of an X. That would be the input. It's also called the term number. And then often we use letters from the beginning of the alphabet instead of like F, G, or H. We use like A, B, C, or D for the output variable for the term. But the more significant thing is, instead of using the parentheses notation, f of x, we'll use a sub k instead of a of k. So, for example, we might write out the first part of the table for the sequence a sub k equals 2 times k. You can do this. Go ahead and press pause and do this now. Okay, so we know what the k's are. They start with 1, 2, 3. They're the natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. And they keep on going forever because we didn't say that this is a finite sequence. It could go on forever. And the a sub k's, or a's, or outputs, are just twice what the inputs are. So they're 2, 4, 6, 8, 10, 12, 14, so forth. Now, since the domain is automatic, if I did another sequence and said do the same thing, we wouldn't have to redo the first line because it's automatically the same. We just have to replace the appropriate things in the second line, no matter what this function is, no matter what this sequence is. So as soon as it's a sequence, notice that it automatically has this same domain. So sometimes we'll just not even write the first line, and instead of writing it in a table, we'll just separate the terms, that is the outputs, with commas. And so you might see this sequence written as 2, 4, 6, 8, 10. So 2, comma 4, comma 6, comma 8, and so forth. And we'll see it written that way. And so this, what you're seeing here, is basically the second line of our table. In other words, our outputs in order. And we don't have to write down the inputs because we know what they are. For the first one, the input is 1. The second one, the input is 2. And it's input 3, 4, 5, 6, 7, and so forth. And we just have to count to know what the input is. So if we want to know what the input is for a 14, we just count 1, 2, 3, 4, 5, 6, 7. It's the 7th term. The term number is 7, so the input is 7. The output is 14. So what we'd like to do here is write out the first 10 terms of the following sequences. These are given as explicit formulas, and you should be able to do this. Press pause, do this now, and come back. Well, so let's see. If a sub k is 3 times k, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, 3 times 6 is 18, and so forth, all the way up to 3 times 10, which is 30. Of course, this actually goes on forever if it's an infinite sequence, but I said just list the first 10 terms of it. Or if this was a finite sequence and it only had 10 terms, this might be the whole thing. B to the k is 2 to the k. Well, let's see. 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16. And you might notice some patterns going along here. For example, in this first one up here, how can we get from one term to the next? Can we just add 3 each time? And in the second one, how can we get from one term to the next? Multiply by 2 each time? Yeah, that works. How about the next one? 3 times k squared. If k is 1, 1 squared is 1 times 3 is 3. K is 2, 2 squared is 4 times 3 is 12. K is 3, 3 squared is 9 times 3 is 27. K is 4, 4 squared is 16 times 3 is 48, and so forth. We'll do the last one. 10 squared is 100 times 3 is 300. I plus 1 divided by 2, so that's 1. Plus 1 is 2, divided by 2 is 1. Put in 2, 2 plus 1 is 3 over 2, so that's 3 halves, or 1.5. Put in 3, 3 plus 1 is 4, divided by 2 is 2, and so forth, and we see that. Notice this one is going up by a half each time. Notice this negative 1 to the j is going to make it alternate signs. When j is an odd number, negative 1 to an odd number is negative 1, so you're going to get a negative number for the output. But when j is an even number, negative 1 to an even power is positive 1, and so we're going to get a positive number. So it alternates negative, positive, negative, positive, negative, positive, negative, positive. And then the absolute value then is just the j plus 1. So 1 plus 1 is 2, but it's negative. Then you do 2 plus 1 is 3. So the numbers just go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, the absolute values, but they alternate signs. Now we have another way of doing this. So the examples that we had for writing out the terms of the sequences before were what I call an explicit way of writing it, a non-recursive way. We could also do this by what's called a recursive definition. We have an initial condition or conditions that explicitly state out the first, or maybe the first few, terms, and then a recursive relationship that states how we get from one term, or perhaps an earlier terms, to the current term. So think of this as like 2 steps. It's kind of like climbing a ladder. The initial condition tells you how to get on the first rung of the ladder, and then the recursive relationship tells you how to climb from one rung of the ladder up to the next rung. So, for example, if we want to start with the first term of 3 and then add 2 each previous term to get the next term, that would be one way to do it. We'd start with 3, add 2 to get 5, add 2 to get 7, add 2 to get 9, and so forth. The way we would write that is a sub 1 has to equal 3. So that tells us exactly what a sub 1 is, the first term, 3. And then we would say a sub k is a sub k minus 1 plus 2. So make sure we understand this. So suppose we want to find a sub 4. Okay, 1, 2, 3. Well, it turns out to be 9 here according to this. Suppose we don't know that yet. We have to know what a sub k minus 1 is. Well, we're looking for a sub 4. K minus 1 is 3. So that would be a sub 4. So you back up. 4 minus 1 is 3. So it's a sub 3. You back up 1, find that a value, which is 7, and add 2 to it to get 9. And that gives us our term. And of course this works for any k bigger than 1. So there's not technically an a sub 0 term. So this formula doesn't make sense when k is 1, so that's why we have to specify where we start. We could get the same kind of pattern, but started at a different point by changing this initial condition. So that's a recursive notation. So here are 3 different sequences. See if you can go ahead and figure out what the sequence would be for this. So let's write out about 10 terms here. Go ahead and figure this out now. Press pause. Okay, so the first one says we start with the first term of 4, and to get the next term, each term we add 3 to the previous term. So we start with 4, add 3 to get 7, add 3 more to get 10, add 3 more to get 13, and so forth. The next one says we start with the first term of 3, and we multiply by 2 each time to get the next one. So 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48. This first one where we're adding the same number each time, that's called an arithmetic sequence. We'll study about those quite a bit in our second unit. And the third one is where we multiply by something each time. That's something we're going to study quite a bit in our fourth unit. That's called the geometric sequence. This last one has a special name too. It's called the Fibonacci sequence. It's pretty famous. It occurs in nature too. In this case, we set up B1 and B2 are both 1. So we set up the first 2. To find one term, the next term, for terms 3 and up, we take the 2 previous terms and add them together. So 1 plus 1 is 2. That's the third term. To get the fourth term, you take the 2 previous terms, 1 and 2, and add them together to get 3. Add 2 and 3 to get 5. Add 3 and 5 to get 8. 5 plus 8 is 13, and so forth. And that's how we generate the Fibonacci sequence. Now, let's see if we can notice a pattern that's in these here, and see if you could write down both a recursive and a non-recursive formula for these two sequences. Now, the formula that you write for recursive formula and a non-recursive should agree with each other and should agree with all the numbers you have here, and you should be able to use that to extend to the next couple of terms. In fact, go ahead and extend this out to a couple more terms. Go ahead and figure this out now. Press pause. Okay, so actually, if you're only given a certain number of terms, there are many ways to extend this so that they agree. So there's not really just one answer to this. As long as your formula accurately gives the answers for what you have there and it can be extended, it's fine. But here's one way to do it, and let's take a look at this. So this first one says we start at 2 and we add 5 to each previous one. So see if that works. 2 plus 5 is 7, 7 plus 5 is 12, 12 plus 5 is 17, 17 plus 5 is 22, 22 plus 5, it's supposed to be 27 there. Sorry, not 37. That's what I meant to do. So if that was 27, this would work. With 37, that doesn't work. Let's pretend it's 27 and do it that way. Then that would work. And then if that is the case, then it could be also written as 5 times k minus 3. So 5 times 1 is 5 minus 3 is 2. 5 times 2 is 10 minus 3 is 7. And so forth, and that will work out. So if that does right, the next terms, so after 22 is 27, then 32, and then, let's see, no, after 22 is 27, then 32, then 37, and then the next ones after that would be 42 and then 47. Okay? And this one down here, one way you could do this is say that we multiply by 3 each time. So B1 is 2, and BK is 3 times BK minus 1. So 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54, 54 times 3 is 162, 162 times 3 is 486, and so forth. So the next one will be whatever 3 times 486 is. And that one could be written explicitly as 2 times 3 to the k minus 1. So when k is 1, 1 minus 1 is 0, 3 to the 0 is 1, times 2 is 2, so that works out to be 2. When k is 2, 2 minus 1 is 1, 3 to the first power is 3, times 2 is 6. Next, k is 3, 3 minus 1 is 2, 3 to the second power is 9, times 2 is 18, and so forth. That's not the only way you could do these, but that's one way that would work if we fix this 37 to be a 27. A series is the sum of the terms of a sequence. So I'm going to introduce a couple of notations here. One is called summation notation, and that means we're going to use a capital Greek letter sigma to represent sum. Sigma is like a Greek version of an S for sum, which means basically add them up. And so we have this notation here, the sum from k equals 1 to n of a sub k means you take the k, let it be 1, so that would be a1, and then k is 2, and 3, and 4, and 5, and so forth, up to the top number of n, and then you add those up. So, for example, if it's the sum from k equals 1 to 4 of k squared, we take k squared, let k be 1, so that's 1 squared. KB2, which is 2, then we get 2 square. Like KB3, which is 3 square. At KB4, so they keep going up by ones. K equals 4, so this is 4 square, and that's the last one, and we're adding those up. So figure these out individually. That's 1, 4, 9, and 16. Add those up to be 30. This is called summation notation. Similarly, we can have product notation where we use a capital Greek letter pi, which looks like this. Lowercase pi is a special number that's the circumference of a circle divided by its diameter, about 3.1415, etc. But this capital pi is like Greek letter P for product, or multiply them together. And it works the same kind of way. So again, if I take k squared again, but say the product from k equals 1 to 4, again we do 1 square, 2 square, 3 square, 4 square, get 1, 4, 9, and 16, but this time we multiply them instead of adding them together. So see if you can evaluate these expressions on your own. Press pause and come back when you're done. Okay? So if we're summing from 1 to 10k, this is just k is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and add those up to get 55. 2k minus 1, and you sum it from k equals 1 to 5, that is, you plug in a 1, you get 2 times 1 minus 1 is 1. Then you plug in k is 2, 2 times 2 is 4, minus 1 is 3, and so forth. So you get 1, 3, 5, 7, and 9, and add those up is 25. The product of k, just k, from 1 to 6 is 1, 2, 3, 4, 5, 6, all multiplied together, which is 720. If we take k cubed and do the product from k equals 1 to 4, we plug in a 1, 2, 3, 4. We cube them to get 1, 8, 27, and 64, and they multiply together to get 13,824. So after studying this lecture, you should be able to define a sequence and series, determine a specific term of a sequence given by a recursive or explicit formula, recognize and extend some patterns in sequences, perhaps even coming up with either a recursive or a non-recursive formula, and demonstrate an understanding of summation and product notation.